Hello my friends, and welcome back to the You Can Do TV channel. The construction of Norwegian Joy, a breakaway plus-class cruise ship of Norwegian Cruise Line, NCL, was an extraordinary engineering achievement at Meyer Werft Shipyard in Papenburg, Germany. With a gross tonnage of 167,725, a length of 325.9 meters, and capacity for 4,622 passengers and 1,821 crew, the ship was initially tailored for the Chinese market before adapting to the US market. The construction process, spanning planning to delivery, combined cutting-edge technology, rigorous project management, and innovative design to create a vessel that redefined luxury cruising. The project began in 2014, when NCL commissioned the ship for approximately 700 million euros. Teams of engineers and designers developed detailed plans, incorporating unique features like a 2-level go-kart track, an expansive casino, 29 dining options, and a 180-degree observation lounge. Originally named Norwegian Bliss, the ship was renamed Norwegian Joy in October 2015, with design tweaks to resonate with Chinese culture, including a phoenix artwork on the hull by artist Tan Ping, symbolizing renewal and prosperity. Construction kicked off with the steel cutting ceremony on September 16, 2015. Using a modular construction method, 80 large steel blocks were prefabricated and assembled with precision. The keel laying ceremony in April 2016 marked the placement of the first block, accompanied by a ceremonial coin placement for good fortune. By June 2016, a 120-meter hull section was launched, setting the stage for further assembly and outfitting. In September and October 2016, two minor welding-related fires caused 50,000 euros in damage and affected several cabins. Meyer Werft swiftly resolved these setbacks, maintaining the project timeline. In March 2017, Norwegian Joy was floated out and embarked on a 14-hour journey down the Ems River to Eemshaven. North Sea trials rigorously tested the ship's 5-man diesel engines, 102,900 horsepower, ABB Azipod XO propulsion systems, and exhaust gas scrubbers for environmental compliance. The interior was completed with high-end amenities, including immersive entertainment venues and luxurious accommodations. Delivered to NCL in April 2017 in Bremerhaven, Germany, the ship was christened in Shanghai in June 2017 by Chinese singer Wang Lihong. After 2 years in the Chinese market, Norwegian Joy underwent a $50 million refurbishment in 2019 to serve the US market, adding the Vibe Beach Club, thermal suite, and enhanced recreational facilities. The construction process, involving thousands of workers and millions of man-hours, showcased unparalleled coordination, innovation, and adaptability, cementing Norwegian Joy as a pinnacle of modern maritime engineering and luxury travel. One of the most modern cruise ships from Norwegian Cruise Line was built at Meyer WERFT Shipyard in Papenburg, Germany. Part of the Breakaway Plus class, it has a gross tonnage of 168,028 GT, a length of 333.3 meters, a width of 41.4 meters, and can accommodate over 4,000 passengers with 1,716 crew members. The construction process began in late 2016, utilizing advanced modular shipbuilding techniques. Large steel blocks were pre-assembled with interiors and equipment before being joined together in a covered dock. After completing the hull, the ship was floated out and transferred via the River Ems for sea trials. The official delivery took place in April 2018. Designed specifically for Alaskan itineraries, Norwegian Bliss incorporates environmentally friendly technology, such as advanced emission control systems and fuel-efficient engines. A standout feature of the ship is its two-level go-kart racetrack, one of the first at sea in North America, stretching nearly 300 meters. Additionally, the ship boasts outdoor laser tag, a multi-level water park, a Broadway-style theater, and over 30 dining and bar options, offering an exceptional cruising experience for guests. In November, a major milestone was achieved during the construction of Icon of the Seas, when its 363-ton aquadome was lifted into place, setting new records. At 50 meters wide and 25 meters tall, the aquadome is the largest glass and steel structure ever to be lifted onto a ship. The entire operation took over 80 hours to complete. The aquadome is part of Icon's 8 distinct neighborhoods, offering 220-degree ocean views, dining options, and the unique aqua theater. Additionally, Icon of the Seas is powered by 6 LNG engines, making it one of the most eco-friendly cruise ships, with features like fuel cell technology, shore power, and advanced waste management. The S-81 submarine, also known as the Isaac Peral, is a key milestone in Spain's naval capabilities, being the first submarine in the S-80 class developed by Navantia for the Spanish Navy. This submarine, named after the Spanish inventor Isaac Peral, who is known for his pioneering work on early submarines, reflects the country's commitment to advancing naval defense technology. The submarine was officially launched on April 22, 2021, in a grand ceremony at the Navantia Shipyard in Cartagena, Spain, marking a significant achievement for both the Spanish Navy and Navantia. The S-81 Isaac Peral is a diesel-electric attack submarine that integrates modern air-independent propulsion (AIP) technology, which allows the vessel to stay submerged for extended periods without the need to surface. This advanced propulsion system enhances the submarine's stealth capabilities and operational endurance, making it more difficult to detect by adversaries. The S-81 has a length of 70 meters, a beam of 7.3 meters, and a submerged displacement of approximately 3,000 tons, making it a formidable vessel in underwater warfare. Equipped with state-of-the-art sonar, radar, and communication systems, the S-81 can effectively detect enemy vessels and launch torpedoes and missiles, providing the Spanish Navy with enhanced offensive and defensive capabilities. The submarine is designed for a crew of 32 personnel, ensuring optimal performance during long-duration missions. Its primary missions include covert surveillance, anti-shipping operations, and intelligence gathering, making it highly versatile in a range of naval combat scenarios. The launch ceremony of the S-81 was a prestigious event attended by key officials from the Spanish government, the Spanish Navy, and Navantia, celebrating the successful culmination of years of research, design, and construction. The event highlighted Spain's efforts to modernize its naval fleet and bolster national defense. Following its launch, the S-81 will undergo a series of tests and trials to ensure its operational readiness before joining the Spanish Navy's active fleet. The S-81 Isaac Peral symbolizes Spain's dedication to strengthening its naval defense capabilities, positioning the country as a significant player in global naval technology. This cutting-edge submarine will significantly enhance Spain's ability to protect its waters and maintain maritime security on a global scale. The S-81 Isaac Peral submarine has successfully moved out of the submarine weapons section, marking a significant milestone. This transition indicates that the integration and testing of its weapons systems, including torpedoes and missiles, are complete. The submarine is now entering its final testing and trial phase, ensuring its readiness for operational deployment with the Spanish Navy. Allure of the Seas, one of the world's largest cruise ships, recently entered dry dock at Navantia Reparaciones Cadiz San Fernando for much-needed maintenance and upgrades. Strategically located in the Bay of Cadiz, Spain, near the Strait of Gibraltar, Navantia is a leader in the repair and refurbishment of large vessels, especially cruise ships, and is one of the most advanced shipyards in Europe. The shipyard is part of the Navantia Group, which is globally recognized for its expertise in shipbuilding, particularly military and civilian vessels. Over the years, Navantia has specialized in the maintenance of large cruise ships, having worked on such renowned ships as the Norwegian Spirit and Explorer of the Seas. The shipyard's strategic location means that cruise ships traveling between the Mediterranean and the Caribbean do not have to deviate too far from their course to undertake necessary repairs. Navantia Cadiz boasts a dry dock measuring 186 meters long, 66 meters wide, and 9 meters deep, capable of accommodating vessels up to 440,000 tons. This makes it one of the largest and most capable dry docks in the region. The shipyard is equipped with state-of-the-art facilities, including cranes with lifting capacities of up to 100 tons, ensuring the efficient handling of complex repairs. The shipyard also has a state-of-the-art water treatment plant, which can process up to 500 tons of gray and black water per day, along with a continuous supply of seawater and fresh water to ensure that the ship's critical systems, such as air conditioning and fire protection, continue to operate during maintenance. Furthermore, the 66 meters of space in the yard below the crane allows for greater flexibility when handling large-scale repairs, such as work on propulsion systems, stabilizers, and paintwork. With a highly skilled workforce of over 250 professionals and the capacity to expand to 12,000, Navantia also excels in providing specialized services such as prefabrication, assembly, and testing of components, including aluminum blocks and scrubbers. The shipyard operates around the clock, providing 24/7 service to meet customer deadlines and demands, ensuring high-quality standards and environmental compliance. The design and construction of the Appomattox oil platform is a monumental achievement in engineering, designed to endure for 40 years. With a height of 16 stories, a width of 2 football fields, and a weight surpassing that of an aircraft carrier, the platform is one of the largest in the world. The project took nearly 4 years of meticulous design work, involving hundreds of engineers who faced unique challenges, such as ensuring the platform could withstand the harsh conditions of the Gulf of Mexico. One of the most significant challenges was ensuring the platform would last for 4 decades, which is double the lifespan of typical oil platforms. Appomattox would be exposed to some of the worst weather conditions, so its construction needed to be of the highest quality. The platform is located 80 miles off the Louisiana coast, in water over a mile deep. This required the design of a floating structure that could support the extraction of oil from wells 14,000 feet below the seabed. In a push for sustainability, the platform was designed to be fully electric, reducing emissions by 25%. The team optimized energy efficiency by utilizing natural gas and steam turbines. They also faced environmental challenges, such as sourcing enough water for cooling without impacting marine life. By drawing water from a deeper, colder part of the Gulf, they were able to minimize environmental impact while meeting the platform's needs. The construction process involved assembling large modules onshore, which were then lifted and stacked with precision by gigantic cranes. The platform's components, including power, oil processing, utilities, and living quarters, were carefully designed to last for decades, with some innovative solutions such as using specialized insulation and extractable chemical storage tanks to ensure long-term durability. The Appomattox platform is a testament to human ingenuity, combining cutting-edge technology, sustainability, and resilience to meet the challenges of offshore oil production for the next 40 years. Offshore pipeline installation is a sophisticated and highly coordinated engineering process used to transport oil, gas, or other fluids from subsea reservoirs to onshore facilities or between offshore platforms. The operation begins with a detailed seabed survey using sonar and geophysical tools to analyze underwater topography and environmental conditions. Based on this data, engineers design the pipeline route, taking into account length, depth, materials, and pressure requirements. Onshore, the pipes, usually made of steel or composite materials, are manufactured, coated with anti-corrosion protection, and thermally insulated if necessary. These pipes are then transported to the offshore location using specialized vessels. Installation is carried out by pipelay vessels, employing methods such as S-lay, J-lay, or reel-lay chosen based on water depth and technical challenges. Pipe segments are welded together, inspected for quality, and gradually lowered to the seabed with precise tension control to avoid structural stress. After installation, the entire pipeline is subjected to thorough inspection, including non-destructive testing, hydrostatic pressure testing, and internal cleaning using pipeline pigs. In certain conditions, especially in shallow or high-traffic waters, the pipeline is buried using plows, trenching machines, or water jetting to protect it from external forces such as currents, anchors, or fishing activities. Each stage of this process requires careful planning, advanced technology, and strict compliance with environmental and safety regulations. With proper execution, offshore pipelines can function efficiently and safely for several decades in some of the harshest marine environments on Earth. The process begins with an aerial view of the world's most technologically advanced cruise shipyard, Quantum of the Seas, highlighting its massive scale and high level of industrial organization. The design phase uses state-of-the-art 3D virtual reality (VR) labs, where engineers and executives collaborate using digital models of the ship. This immersive technology allows the team to simulate and review every detail of the ship's layout and functionality before actual construction begins. In the laser hall, large steel panels are automatically moved into place and precisely laser cut in preparation for assembly. These panels form the basis of the ship's structure and are manufactured with high precision to minimize errors and waste. This is followed by the block assembly phase. The ship is built from prefabricated blocks, each transported by remote-controlled vehicles and heavy-duty cranes. The blocks are then lifted and assembled inside the building hall, a massive, self-contained facility designed for shipbuilding. A time-lapse video shows the gradual construction of the ship, including major structural components such as the keel, stern, and bow. Inside the workshop, propellers and propulsion systems are also installed. Skilled workers perform critical assemblies as the ship takes shape. Meanwhile, at EMS's pre-cab cabin factory, modular cabin units are manufactured separately. Workers install wiring, plumbing, and bathroom fixtures. Each cabin is completely completed off-site, including quality control tests. Once ready, the cabins are transported to the ship and installed directly by crane, significantly speeding up the construction schedule. The finished cabins are then installed, transported, and aligned with mechanical precision inside the hull. Finally, Quantum of the Seas is moved out of the shipyard, ready for sea trials and final installation. A stunning time-lapse sequence shows the entire construction process, from the first steel cut to the completed ship leaving the shipyard. The clip ends with Quantum of the Seas and Anthem of the Seas built side by side, highlighting Meyer Werft's ability to produce world-class cruise ships using modern design tools and highly efficient modular construction techniques. The construction of the Ada Cosma, a modern cruise ship built by Meyer Werft in Germany, involves a detailed, step-by-step process combining advanced technology and sustainable practices. The process began with 3D design and simulation, where engineers and designers created detailed plans for the ship's structure and passenger amenities, optimizing aspects like fuel efficiency and space. After the design phase, the production began with steel cutting using state-of-the-art technology, followed by the assembly of massive steel blocks. These blocks were pre-equipped with systems like pipes and electrical components before being transported and assembled in a dry dock. Once the hull was completed, the dry dock was flooded, allowing the ship to float for the first time. The ship was then moved to an outfitting dock where the interior, including restaurants, bars, entertainment areas, and advanced technology systems like Starlink Internet, were installed. After the ship's structure and amenities were fully in place, it underwent sea trials to test everything from engine performance to navigational capabilities. The Ada Cosma is equipped with sustainable features, including being powered by LNG, reducing harmful emissions. It is also one of the largest ships in the world, measuring 337 meters in length and carrying over 6,000 passengers. The ship boasts numerous amenities, such as 17 restaurants, 17 bars, 6 pools, and more than 1,000 square meters of shopping space. It also offers 2,732 cabins in various categories, from suites to rooms with balconies. After successfully completing the trials, the ship was officially handed over to AIDA Cruises, where it began its operations, mainly sailing in the Mediterranean. This process highlights the meticulous work involved in building a luxury cruise ship that blends high-end design with eco-friendly technology. Many years ago, Meyer Werft achieved several important milestones, affirming its advanced technical capabilities and leading role in the global cruise shipbuilding industry. One of the most notable highlights was the delivery of Norwegian Joy to Norwegian Cruise Line in April. This is a breakaway plus ship, with a gross tonnage of up to 168,800 GT, a length of 333 meters, and a capacity of more than 4,200 passengers. The ship was specially designed for the Chinese market, and is one of the first cruise ships to feature a double-deck go-kart track at sea. The completion of this ship marks Meyer Werft's success in combining bespoke design with precise mass production. The Mein Schiff series, operated by TUI Cruises, is a premium fleet designed for German-speaking travelers seeking comfort and relaxation at sea. The fleet began with Mein Schiff 3 in 2014, followed by Mein Schiff 4, 5, and 6, each offering spacious staterooms, many with balconies, and a focus on wellness, dining, and entertainment. The newer Mein Schiff 1 and 2, launched in 2018 and 2019, are larger and more advanced, with a gross tonnage of over 111,000 and capacity for nearly 2,900 passengers. In 2024, Mein Schiff 7 joined the fleet, continuing the modern design and passenger-focused experience. All ships feature elegant interiors, open pool decks, and state-of-the-art facilities, reflecting TUI Cruises' commitment to high-quality, environmentally conscious cruising. Iona's construction is a feat of modern shipbuilding. It begins with a detailed design phase, using advanced 3D modeling and virtual simulations to refine the ship's structure and onboard experience. Once complete, the first steel block is cut, marking the beginning of the physical construction process. The ship is built using a modular approach, in which large steel sections called blocks are prefabricated, then lifted and assembled in a dry dock like giant Lego pieces. Each block comes pre-fitted with systems such as piping and wiring, streamlining the integration process. Once the hull is complete, the dry dock is flooded to float the ship for the first time, and Iona is transferred to the assembly dock for interior fittings and finishing touches. The final steps include extensive sea trials to test all onboard systems and open ocean performance. Having successfully passed all tests, Iona officially joins the P&O fleet, marking a new era in sustainable luxury cruising for the UK market. MS Iona is P&O Cruises' flagship and the largest cruise ship built for the UK market. Delivered in October 2020, Iona was built by the renowned Meyer Werft Shipyard in Papenburg, Germany. Measuring 344.5 meters in length and weighing 184,089 tons, the ship can accommodate up to 5,206 passengers and 1,762 crew. Iona is also notable for being the UK's first cruise ship to be powered by liquefied natural gas, LNG, a cleaner alternative to conventional marine fuels that significantly reduces emissions. The ship features a host of amenities including 17 restaurants, 12 bars, 4 pools, and the iconic Sky Dome, a 970 square meter glass entertainment venue. Norwegian Encore is the fourth and final ship in Norwegian Cruise Line's Breakaway Plus class, built by Meyer Werft in Papenburg, Germany. The ship was launched on the 17th of August 2019. At 333.5 meters long and 41.5 meters wide, Norwegian Encore boasts a gross tonnage of 169,116 GT. The ship can accommodate up to 3,998 passengers in double occupancy and is served by a crew of approximately 1,735. Powered by a diesel-electric propulsion system, the ship is powered by 5 MAN B and W engines with a total output of 102,900 horsepower, 76.7 megawatts. This setup enables a service speed of 22.5 knots, with a top speed exceeding 25 knots during testing. The propulsion system includes 2 ABB AZPod XO units, enhancing maneuverability and efficiency. The ship's amenities are designed to cater to a wide range of guest preferences. Notable features include a 350-meter go-kart track, the longest at sea, and a wide range of dining options at 19 restaurants, including 13 signature venues. During the anchor deployment, only 3 shots, 270 feet, were supposed to go out, but an issue with the brake knot setting caused the chain to be deployed until about 600 feet was released. When the chain turns red, it signals that only 90 feet remain, which meant the situation was just a few feet short of a disaster. In nautical terms, a runaway anchor refers to one that is out of control, as in this case. The crew handled the situation effectively, with the person at the front standing at parade rest, awaiting the whistle to raise the Union Jack, signaling that the vessel was anchored. In May, the vessel Guardian arrived at Navantia facilities for a major repair project involving the replacement of its main engine bedplate. This operation began after cracks were discovered on the bedplate during the vessel's last dry docking in the summer. The shipowner, ConoPhillips, awarded Navantia the contract for the bedplate renewal in April. Upon the vessel's arrival at the shipyard, an initial coordination meeting took place to review safety procedures. After conducting gas-free tests, the repair work commenced immediately. The dismantling process started with the removal of key engine components such as pistons, connecting rods, crosshead assemblies, cylinder liners, and cylinder heads. These parts were sent to the workshop for inspection and evaluation by both the shipyard staff and a specialized team of engineers. A critical milestone in the project was the arrival and intermediate storage of the new bedplate. As dismantling continued, the next step involved assembling the necessary structure and equipment to lift the engine and remove the damaged bedplate. A specially designed frame structure, equipped with 2 pairs of hydraulic jacks capable of lifting 340 tons, was used for the hoisting process. This setup ensured complete safety, with dual protection mechanisms that allowed work to be carried out underneath the load. Once the upper engine section and crankshaft were hoisted, the vessel was moved to the dock. The damaged bedplate was carefully removed and replaced with the new one using a turntable and a skidway system made of Teflon sheets, enabling controlled movement over uneven surfaces. After the bedplate was in position, the crankshaft was lowered, and all internal and external engine components were reassembled. Following the final adjustments, including machining the shaft flange to correct initial misalignments, comprehensive checks and trials were conducted. This included the centering of the shaft seals and verifying engine and navigation parameters. After successful completion of all tests, the 70-day project was concluded, with the Guardian ready for sea trials, ensuring both client and team satisfaction. The project's efficiency and the high quality of work further solidified Navantia's reputation in the maritime industry. RC-1200T Goliath crane. With an impressive lifting capacity of 1,200 tons, this crane can reach a maximum lifting height of 90 meters. The crane operates on a rail length of 154 meters, and has an impressive total height of 120 meters. It can travel at a speed of 30 meters per minute, facilitating efficient handling of large structures. In addition, the crane is equipped with a rail length of 750 meters for operating tower cranes. Construction of USS Gerald R. Ford, CVN-78. The lead ship of the United States Navy's class of nuclear-powered aircraft carriers. Built at Newport News Shipbuilding in Virginia, the project involved approximately 5,000 shipbuilders at its peak. Construction began on August 11, 2005, followed by a keel-laying ceremony on November 13, 2009. The ship was launched on October 11, 2013, and commissioned on July 22, 2017. At 1,110 feet long and displacing approximately 100,000 tons at full load, the Gerald R Ford represents a number of technological improvements over its predecessors. Notably, it uses an electromagnetic aircraft launch system, EMALS, and advanced arresting gear, AAG, replacing the traditional steam catapults and arresting gear. These systems allow for more efficient and less stressful aircraft launches and recoveries. The ship is powered by two A-1B nuclear reactors, providing virtually unlimited range and allowing for a top speed in excess of 30 knots. Its air wing can support up to 90 aircraft, including the F-35C Lightning II, enhancing the carrier strike capabilities. The Gerald R Ford faced challenges during its development, particularly with the integration of new technologies such as the Advanced Weapons Elevator (NAPE) and the Complex Carrier Refueling and Overhaul (RCOH). This monumental undertaking was described in a 2002 RAND study as one of the most challenging engineering and industrial undertakings any organization has undertaken. The USS Gerald R Ford is a testament to modern naval engineering, combining increased efficiency, advanced technology, and improved capabilities to project power globally. The Icon of the Seas, the world's largest cruise ship, features 2,800 rooms, 22 elevators, and weighs over 250,000 gross tons. Built by Meyer Turku Shipyard in Finland, this floating megastructure took over 2.5 years to complete. Construction began after virtual simulations at Royal Caribbean's high-tech lab in Miami, followed by traditional steel cutting and keel-laying ceremonies. Engineers assembled the ship block by block, stacking giant pre-built sections like a massive puzzle. Once the hull was complete, the ship was moved to an outfitting dock, where interior features like furniture and decor were installed. It underwent sea trials to test engines, steering, and systems. At 5 times the size of the Titanic, and taller than the Eiffel Tower, the ship floats due to its U-shaped hull, which ensures stability and buoyancy. Made of high-strength steel and featuring open, airy spaces, the design balances weight and displacement, making it a marvel of modern maritime engineering. The salvage operation to recover the Russian nuclear submarine Kursk from the Barents Sea was one of the most challenging and remarkable feats in modern maritime history. The Kursk, a nuclear-powered submarine, tragically sank after a massive explosion during a military exercise on August 12. All 118 crew members on board perished, and the disaster shocked the world. The recovery of the wreck was crucial, not only for retrieving the submarine, but also for bringing closure to the families of the victims. The operation, which took place between 2001 and 2002, involved a massive international effort that combined technological innovation, meticulous planning, and extraordinary engineering expertise. The Kursk sank to a depth of 108 meters on the seabed, approximately 70 miles off the coast of the Russian region of Murmansk. The submarine, which measured 155 meters in length, was severely damaged in the explosion, with its nose section buried in the seabed clay. The Russian government contracts MAMO, a global heavy lifting and transport company, to lead the salvage operation. Mamoet, in partnership with Smith International, formed a joint venture to carry out the operation. The project requires meticulous planning and extensive international cooperation, as the Kursk was one of the largest and most challenging recovery operations ever attempted. The preparation for the operation was immense. The lifting units, which were custom-built for the operation, were fabricated and tested in various locations around the world. The project involved hundreds of engineers and technicians who worked tirelessly to ensure the equipment would function as planned. The lifting cables, which would extend over 200 kilometers, were carefully wound onto enormous reels to prevent tangling during the operation. Additionally, a specially designed cutting wire was created to sever the submarine's damaged nose section, which had to be removed before the lifting could begin. This cutting wire, made of steel thread with specially processed bushels, underwent extensive testing to ensure its ability to withstand the immense pressure and harsh conditions of the sea. The cutting operation involves a highly specialized technique known as abrasive jet cutting. Divers, working from a support ship called the Mayo, were tasked with cutting 26 holes in the submarine's hull, using high-pressure water mixed with sand to create the necessary openings. The divers worked in teams, rotating every 6 hours to ensure that the job was completed as quickly as possible. This part of the operation was critical, as the holes had to be precisely cut to allow the grippers to attach securely to the Kursk's frame. Another challenge the team faced was the potential danger of radiation leakage. Since the Kursk was a nuclear submarine, it was equipped with 2 nuclear reactors. A team of radiological protection experts from the UK and Belgium monitored radiation levels throughout the operation. Their presence ensured that no radiation leaked from the submarine during the recovery, which was essential for the safety of the personnel involved in the operation. Fortunately, the reactors were safely contained, and no radiation was detected in the surrounding environment. Once the cutting of the Kursk's hull was completed, the salvage team was ready for the critical lifting phase. The 26 grippers, which had been positioned around the submarine's hull, were carefully connected to the strand jacks on the barge. The heavy compensators, which act like shock absorbers, were also put into place to help control the tension in the lifting cables and stabilize the operation as the barge rose and fell with the waves. The lifting process was slow and deliberate, as the team had to ensure that the force exerted on each attachment point remained constant to prevent instability. The team encountered several challenges during the lifting operation. The unpredictable weather conditions, including gale force winds and heavy seas, forced the operation to be temporarily halted. However, once the weather improved, the lifting continued. On October 8, 2001, after hours of careful lifting, the Kursk was only to be freed from the seabed. The 9,000-ton submarine began to slowly rise to the surface. The operation was extremely stressful, as any mistake could have caused further damage to the submarine or caused the entire operation to fail. However, despite the risks, the lift was successful, and the Kursk was eventually secured to a barge, ready to be transported to Murmansk for final restoration. The journey to Murmansk was another crucial stage of the operation. The barge carrying the Kursk had to navigate the rough waters of the Barents Sea to reach the Russian port. Once there, the submarine was carefully placed in dry dock for further inspection. However, before this could be done, the submarine had to be raised to ensure it could fit in the dry dock. This involved a second lift, using large pontoons that were slowly filled with water to sink them beneath the Kursk. Once positioned below the submarine, the buoys were inflated with air, lifting the entire assembly and allowing it to be moved into dry dock. The entire salvage operation took more than a year to complete. The Tricolor, a massive car carrier owned by the Norwegian shipping company Wilhelmsen and operated by Wilhelmsen Logistics, was a ship that, on December 14, 2002, faced a catastrophic incident in the North Sea. The Tricolor, sister ship to the Tronen, was carrying over 2,800 brand-new cars destined for the American market when it was struck by the container vessel Kiba in the early hours of the morning. The collision caused the Tricolor to capsize and sink within 30 minutes. The incident took place in one of the busiest shipping lanes in the world, which posed a significant threat not only to other vessels but also to the environment due to oil leakage from the vessel's bunker tanks. Despite the severe weather conditions, prompt action by the ship's 24 crew members led to a successful evacuation, and fortunately, there were no casualties. The wreck, however, lay on the seabed, blocking vital shipping lanes and posing a serious environmental hazard. The owner of the Tricolor, Wilhelmsen, acted quickly to prevent further environmental damage. The company prioritized oil spill containment, and the floating shear legs, Asian Hercules II, were deployed to assist in the salvage operation. The Asian Hercules II served as a stable work platform for salvage teams, who began the delicate task of pumping the remaining 2,100 tons of oil out of the sunken vessel. Despite freezing December conditions and strong currents, the team managed to extract the majority of the oil, although some residual oil remained trapped in the ship's tanks and car decks. With the oil removed, the next challenge was to safely remove the wreck itself. The Tricolor was resting on its port side, and attempts to upright the vessel proved to be too dangerous due to its fragility. Consequently, the decision was made to cut the ship into 9 large sections, which would then be lifted and transported for scrapping. The operation involved assembling 2 work platforms on either side of the wreck, positioned at a depth of 30 meters. These platforms allowed the team to carry out the cutting of the wreck using a specialized wire cutting system. This cutting technique was not only unique, but also untested at such a scale. The salvage team employed a special cutting wire composed of small cylinders made from a mix of steel as hard as diamond. After extensive testing, the team began the painstaking process of cutting the ship into sections. Each cut was carefully monitored by divers and surface personnel, ensuring the wreck's structural integrity and safety. The first sections of the wreck, including the stern, were lifted using two of the world's largest floating shear legs. These cranes, capable of lifting immense weights, were used to lift the cut pieces one by one. The first section lifted was estimated to weigh around 3,200 tons, and as each piece emerged from the sea, the team meticulously checked for stability before transporting the sections to a nearby barge. The operation was extremely delicate, as the lifting required careful handling to avoid damage. The lifting process had to be slow and controlled to ensure that the wreck's sections did not collapse. Once each section was securely lifted, it was transported to the port of Zeebrugge in Belgium for scrapping. The remnants of the Tricolor, along with the damaged luxury cars, were dismantled in a specially prepared scrapyard, which had measures in place to prevent environmental contamination. Throughout the entire operation, environmental protection remained a top priority. Authorities from both France and Belgium were involved, ensuring that the seafloor was left as clean as possible. The salvage team employed various techniques, including magnetometers and multi-beam systems, to locate and remove smaller metal pieces and cars that had been washed into the sea after the collision. The experience was a test of reputation and resolve. While the incident was damaging, the successful salvage operation proved that the shipping industry could effectively respond to crises. The submarine cable installation works for the Nordsee 1 offshore wind farm, OWF, in the German Bight North Sea, were carried out by SEAM offshore contractors from June to August 2016. This project involved the installation of 59 IAG cables spanning a total length of 68.0 kilometers with 188 cable pull-ins. The cable supply was provided by JDR Cable Systems, and Seaproof Solutions supplied the CPS, including MP interface units. The installation process began with a pre-lay inspection survey, followed by the deployment of pull-in, termination, and testing equipment. The SEAM Moxie, AULSTEINSX 163 Expo installation support vessel, was used for the deployment of equipment, including a 5-ton winch and motion-compensated crane for precise cable handling. The SEAM Amory, a VARD CLVO-1DP2 cable lay vessel, played a key role in the cable laying process, including subsea crossings and post-lay trenching. The trenching was carried out along a route length of 60 kilometers, with a burial depth of 1.5 meters, using rock berms, mattresses, and PU impact protection. The cable laying involved a 2-end pull-in system, with pre-installed messenger wires used to guide the pull-in line and connect it to the cable pulling head. ROV monitoring ensured accurate touchdown monitoring during the surface laying of the cable. Following the surface lay, careful calculations were made for cable cut positions, and cable markers were applied on board to track the cable's seabed position. The entire installation was meticulously executed, using specialized vessels and equipment, ensuring compliance with DNV GL codes and meeting high standards of safety and precision in offshore cable installation.